So that OneDrive folder on Moodle. There. Have I put it up on Moodle? Okay. I didn't because I'm an idiot. Right. Hang on a moment. Let me just add it in. Close that down. Let's save that. Close this down. Save that. Okay, right. So now there's a link in the announcements part just before the course notes where there is a little link there, and you click on that link. It should bring you to the OneDrive folder, which will have a weekly breakdown of what we've covered each week. I haven't put everything into it for this week because we haven't finished all of the stuff for this week. That's loading slow. But it's in the announcement. If you need to, I've literally just put it in now. So if you're on Moodle, you need to refresh the page. It will pop up at the very bottom of announcements. Okay, so you open up our notepad again. We're going to do two problems now. No, actually, we're just going to do one problem. We'll use a problem using modulus and div to split our code split a number in our code up into component digits. So save this as digits. So to get this working, we need to do a little bit of experimentation. I want to see what happens when I start diving using the div command and modeling using the modulus command and number and see what the outcome is. So we're going to start off with our number, which is going to be 1, 2, 3, 4, 5. And I'm going to div that by 10. And then I'm going to take the same number and I'm going to mod it by 10. Okay, so there are two samples. This one here is, well, we're going to, okay, and that's what we're looking for here. So the first command is going to give us our whole number division. How many times does 10 go into 12,345? It's going to go in 1,234 times. What is the remainder after we have divided that? It's going to be 5. Okay, so let's look at the output we have here. Save that into my command. This is going to be Java C digits. Spelled horrifically. And then we're going to spell it 3 digits. Spelled slightly better. Okay, so there's my output. When I divide 1, 2, 3, 4, 5 by 10, the output is 1, 2, 3, 4. When I use the modulus command on 1, 2, 3, 4, 5, and I modulus by 10, the output is 5. Now my original number is 1, 2, 3, 4, 5. So what these two, the combination of these two commands here have done is they have chopped the first 4 digits off. Sorry, they've chopped the last digit off and left me with the front 4 digits. And they've chopped the first 4 digits off the front of it and left me with the last digit. And that's really interesting, because when I know that, I can adjust what I'm dividing and doing the modulus command on to get different variations of them. So what I can do here is I can go back into my code. I'm going to take this stuff here, copy it, and paste it, and paste it. There, there. So we've done 10 and 10. Let's try 100 and 100. Let's try 1000 and 1000. So I've taken the same command, div 10 mod 10, and then I've done div 100 mod 100, and div 1000 mod 1000. And what you'll see is each of these commands chops that number at a certain point. And changing the divisor by the power of 10 will shift where that chop happens. So we can see here, this removes the last digit. This leaves the last digit and moves the front 4. This, we divide it by 100, will leave me the last 2 digits and remove the last, or sorry, it'll give me the first 3 and remove the last 2. This will remove the first 3 and leave me the last 2. And you can see how that's going to work our way through. So let's save that. Back in here, compile it, and run it. And so now you can see the splits. 1, 2, 3, 4. Left foot 5. 1, 2, 3. Left foot 4, 5. 1, 2. Left foot 3, 4, 5. So we can keep moving that number and keep increasing our divisor by the power of 10. And eventually what will happen is we'll be left with 0 on the integral side. It doesn't go in any times, but 1, 2, 3, 4, 5 on the remainder. So that's something interesting. That allows us to split the values up. If I were to divide this by, let's keep going. Let's do one more time down here. This should be 10,000. This should be 10,000. Save that. Run it one more time. Okay, so let's have a look. This is when our divisor is 10. This is when our divisor is 100, 1,000, 10,000. If we look at the first modulus command, we're left with the last digit, and the last div command, where we're dividing by 10,000, we're left with the first digit. And at that point, we were like, oh, we can get the first digit and we get the last digit. And then what we're concerned with is what's in between. So here's what I'm going to do. I'm going to have a pattern that's going to be one thing for the first digit, because that's easy to do on its own. We can just do this command here. But for the second, third, and fourth digit, I'm going to run a different command each time, and you'll see what happens. So that's my draft there. I'm going to save that, and then I'm going to create a new version, which is a working version. Let's call it digits, first of all, and 2. Up here, we'll call this digits 2. So we have it there. I'm going to get rid of all of this stuff for the moment. I'm going to get rid of the comment for the moment. Okay, so there's our number there. And that's going to give us, that'll just chop off the last digit. That's no use to us at the moment. What we want to do is we want to have the first digit. So if we divide it by 10,000, because we know it's a 5-digit number. 5-digit number means that the most important, the most significant digit here is the 10,000 range. 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000. Okay? It doesn't go up into 100,000. So you divide by 10,000, we're going to be left with just the front digit. So we'll do that, and that's going to give us our first digit. Now, what do I need to do? Well, what I now need to do is I need to start slowly reducing this number down. I've chopped off, the first time I chopped off the last four numbers. I'm left with the first one. That's simple because I'm just looking for the front number. Every other number, it's a 2-action command. The first bit is to chop off one less number than the last time. So this time I chopped off 4. This time I'm only going to chop off 3. So I'll be left with 1, 2. And then I need to get the last number in that new example. So it's going to be, rather than divided by 10,000, it's going to be divided by 1,000. That goes into one set of brackets. And then whatever the answer to that will be, which will be 12, I'm going to go modulus 10. And that will give me a second digit. So what happens here in this command is it takes 12,345 and divides it by 1,000. 12,000 blah divided by 1,000 leaves me 12. Okay, so that's the first part, the bit part of the bracket solved. 12 divided by 10, when I'm only concerned with the remainder, gives me 2. That makes sense? So that's what we have here. The next line down, just get rid of one more. 12,345 divided by 100 goes in 123 times. Modulus 10 just gives me the last digit there, gives me 3. And this continues. Okay, so you can see the pattern. We're dividing, we're using the div command, then we're using the mod command. The mod command never changes. The divisor is always the same. It's always 10. It always gets the last digit. And the div command, I mean, I could actually, if I wanted to, I actually could make this match exactly as it is. Okay, so I can make it look exactly as it is there. Because if I divide 12,000 something by 10,000, it leaves me with 1. And if I say, okay, and if I divide that number by 10, what's the remainder? It's 1. It goes in 0 times evenly with 1 left over. So it'll leave me with 1 there. And what happens here is I divide this number by 1,000, and I'm left with 12, and I get the last, I divide that 12 by 10, and I get 2 as the remainder. Here I divide this number by 100, and I'm left with 123. I divide 123 by 10, it goes in 12 times with 3 left over, the bit I'm looking for. Here I divide this number by 10, and I get 1,234. I divide that number by 10, and I look for the remainder, and I get 4, going in 123 times evenly. And then this one here, 12,345 divided by 1, it goes in 12,345 times. And if I divide that by 10, it just gives me the last digit, it gives me 5. This is really interesting because while I've done this over a series of math commands, we'll see that without using any other extra ways of representing that number, just having it as a literal value, as it's a number, I can specifically target a digit within that number. There are other ways of doing this, but they're long-winded. One way of doing it is converting it into text and then getting the middle character or whichever character you're looking for, and then converting it back into a number. And that's an awful lot of processing power going back and forth. Whereas this one, we're just looking at, we have 2 simple math commands. How can we chop that number up into its component digits? When we cover our variables, which we're going to get onto in a moment, and when we cover our loops and user input, which is in 4 weeks time, we'll be up to that point, I can get you to write a program where the user could enter any number under 1 million, and you could successfully go through it without having to have 7 of these going down. You could have one statement inside a loop, and it would iterate each time, slowly changing this value here or this value here as we work our way through. And it then means if you can do it for 1 million, you can do it for 10 million, you can do it for 100 million, you can do it for 1 billion. If we had a number set big enough, you could do it for 1 trillion, that you could actually chop all those numbers up. Okay, so this is mathematically the most complex thing we've looked at this year, but the commands are reasonably simple. This gets our whole number division part here. This gets the remainder after we've divided by this number. So let's check if it works. So we're going to save our code. Go into our command here. We're going to go Java C digit 2. And then we're going to go Java digit 2. And there we have 1, 2, 3, 4, 5. And if I wanted to reverse that, it would just be putting these printhead statements in the opposite order. Do this one first, and this one, and this one, and this one, and this is the last one. Okay? I'm not sure if that's terror or relief in the faces looking back at me. We're going to take a step away from math for a little bit and come back to it later on, okay? Like I said, programming revolves around math and calculus and algebra. And I'm going to make it worse now by adding letters to your math. So far, this is all the numbers, and if I remember rightly, it's usually when you start adding in letters, solve for x and that type of stuff, it's where people start to really kind of move away from math as a topic. So let's do that. Actually, 4 variables. There we are. And that's 2. Cool. There we go. Okay, so this is the next thing we're adding in. So far, we have been able to do 2 things. We've been able to print text to the screen, and we've been able to do calculations on the screen. My goal now is to make your programs useful, and it will require, we've done step 1, and there are 5 steps in total. The next step is introducing the idea of a variable, a way of storing information. I can calculate those values. But imagine if I wanted to get the middle digit of a 5-digit number. I don't want to go through all that calculation every time. Okay? I want to do it once and then hang on to that number so I can reuse it again. And that's the trick with variables. A variable is a storage area, temporary storage area inside your program. It only exists while your program is running. If you turn your program off, you kill your program, if the program completes, it disappears. And because it's stored on the random access memory of your computer, as soon as you turn your computer off, it's gone. You can't recover the data. So it sounds very temporary, but it's really useful for what we need it for. And in the second semester, we'll look at being able to store information more permanently by writing it to a file. And it actually is stored in your hard drive and it's persistent. You can call it later on at a different time. But yeah, so we have 5 steps. The first step is output, printing to the screen. We've got that done. Or we've mostly got it done. We'll look at revisions as we go along. The next step is variables. Can I store a value in my program as I'm going along? The next step is user input. Can I ask the user for information and then store it in a variable and then do something with it and print it to the screen? The next step after that is a condition. Can I ask my program a question based on a value held inside a variable that the user has given me? And the last step is iteration or loops. Can I do something multiple times? Can I get my user to enter in their name and a number and print that name that number of times on the screen without me having to have 700 printhead statements? Okay, I want to make my code tighter, more efficient. And that's what I'm looking to do. So at the moment, the values we looked at are either literals, which means they're numbers. And what we've seen for numbers, I'm not going to flick back now because it means shutting the presenter and opening it back up again, is that they appear kind of in orange. Numbers generally appear in orange. That means they're a real value, an actual value. It's the number 3. It's the number 3.1415, whatever it might be. And then we have strings. And strings are the things that appear inside our quotation marks. So the hello world or whatever the output might be to your program. We're going to come back to strings later on. I'm going to imagine by the time we hit the end of February, you will be sick of problems that revolve around strings. Because when we get to the point of strings, and we've done loops, and we've done if statements or questions, and we've done user input, I can start coming up with really obscure and weird ways of testing how well you understand what we've covered, and they all revolve around an idea of string manipulation. Here's a bunch of text. I want you to do some stuff to it. Count how many vowels. Count what's the most common letter. Remove all the vowels out of the string. Remove all the vowels and put them into alphabetical order. Take all of the characters you have there, and if it's a paragraph of text, tell me how many words are in that text, how many sentences, what's the average length of the sentence, what's the average length of the word, what's the longest word, what's the shortest word, what's the longest sentence. You will be sick of dealing with strings by the time we hit the end of February, but you will have a really good understanding of systematic processing, going through it, and you just perform a set of actions depending on conditions. But the first step to get there is the idea of variables. So think about what we've just done with our calculations. We've done a calculation for the surface area of a cylinder. Okay, that's a very specific cylinder. It was a cylinder that was 4.25 radius, so that the entire width of the tin would probably 8.5, and it was 8 units high. That's a really, really specific cylinder. What if I had a different cylinder? What if I didn't have a cylinder that was 4.25 and 8? It was like matching in the slides. It was 15 and 10. Well, at the moment, I need to go into my editor, open up the code, edit the code, save the code, compile the code, get rid of errors, run the code, and then I can figure out what the calculation is. That's not particularly useful. If I were to extend that out to our calculator, think about the calculator built inside Windows, or inside your phone, or inside whatever operating system you use. You can open that up and you can type in a number, you can hit a symbol, you can type in another number, solve it for you. Great. You can close it down, you can open up the same program and type in 2 different numbers and use a different symbol, and it solves that problem for you. You can open up a calculator on someone else's computer and put in 2 different numbers and a different symbol, and it still works. That's a useful program. What that means is it's a general problem solver for calculations. Doesn't matter what the calculation is, doesn't matter what the numbers are, doesn't matter the order you put the numbers in or the type of symbols you're using, it can still work, it can still solve that. But at the moment, we don't have that facility on our skills we have. If we want to do that, we would need 1 calculator program for adding up 2 plus 2, 1 calculator program for adding up 2 plus 3, 1 calculator program for adding up 2 plus 4. You can see where this is going. We would have a ridiculous amount of programs to solve our problems. We don't want that. So the way we can get around that is by using something called a variable. So a variable is a storage unit inside programming. It's temporary. It exists while the program is running, and by the definition of its name, the value inside it generally changes through the life cycle of your program. It'll start at one value, it may get changed along the way, and it may be a different value at the end. It doesn't have to, but it has the possibility of changing. It's our first step in making our programs useful. And why it makes it useful is it saves on the brain power that's required by the computer. If you haven't done circuits, you probably haven't done von Neumann modeling of computer hardware. It's coming along, it's fine. But your computer, no matter how powerful it is, no matter how new it is, no matter how much the salesperson said it is the best thing you can buy, it has finite resources. It has a limited amount of memory. Your hard drive is only a certain size. It has a limited amount of working memory. You only have a certain amount of RAM inside it. It has a limited amount of brain functions. The processor is only so big. Yep, of course. The processor is only so big. Even if you buy, what's the most expensive one? The i9 Intel processor, some ridiculously overpriced home version of a supercomputer, you still have a limit on what you can do with that. Okay? When we're writing code, and I know our programs this year are going to be super small, but this is setting the foundation for as we build more complex programs. The reason why we use variables is if I can calculate a calculation that I know I'm going to need multiple times in this program, why should I use that brain power to recalculate it each time? Why don't I store it and come back to it later on? Now, for us as humans, if you had a calculation you had to calculate a couple of times in, let's say, an hour's worth of work, you'd calculate it once, and maybe the second time you calculate it, and one of two things would happen. Either you would recognize the pattern. Oh, I've seen that calculation before, and you'd remember what it was. If you're remembering what it was, it means you have instinctively stored that in your short-term memory, and you can recall it quickly rather than have to do the calculation. Or you get really irritated by having to sit down and do that calculation, which takes however long, and you write it down on a piece of paper. You write this is equal to, and you get the result. And then you don't need to recalculate it. We want to do the same thing here. Computers don't get irritated, they don't get distracted, they don't get tired, but they have a limited amount of resources. And we'll assume that if we can calculate something once, that brain power, the processor cycles, could be better used for other things in the program later on. Once we've done it once, why don't we save it? Why don't we store it? Think about the specs you see on computers when you buy them. This is a 1.2 gigahertz processor. That just means how many things it can do per second. And again, 1.2 gigahertz is an incredible amount of work in a particular second. But you're also running the operating system. You might be running PowerPoint. You might have YouTube open. You might be watching Netflix. You might have services running in the background. Your antivirus. So there's a lot. You don't have that full 1 point whatever it is gigabytes. You would have a portion of that. But then you have your RAM, and that might be 4 gigabytes, or 8 gigabytes, or 16 gigabytes. And then you have your hard drive, which is 200 gigabytes, or 500 gigabytes, or 1,000 gigabytes, a terabyte. And so what's happening is, inside the processor, we have a teeny tiny amount of what's called cache memory. And that's for immediate calculation memory. It is incredibly quick. The reason why we have a teeny tiny amount, I mean something like a 6 megabytes, 12 megabytes, is because it is incredibly expensive to manufacture. The next layer out is our RAM, our random access memory, and there we have gigabytes of it. And you can have. I was looking at laptops for my research, and I saw one that was 64 gigabytes of RAM, which is more than I had in my first 4 computers as a hard drive. So it's kind of ridiculous that you have that much, and your RAM is kind of your working memory. So all the things that are open, all the programs that are open in your computer are using that. And then your hard drive is even bigger again, but it's slower. So what the general rule of thumb is in computing, the faster the memory recall, the faster you can get it, the less you have in the computer. So your cache, which is built into the processor, you have megabytes, a very small amount. Your RAM, which is not built into the computer, it's a stick that you slot into it, but dictates how much your memory can do. So it's kind of like how big is your desktop, your physical desktop you work on. If you're doing all your work on like a serving tray from the canteen, that's a very small amount of RAM. You can't actually have a lot of stuff open. If you have a nice big table like this, that's a lot of RAM. I could have several things open at once and they're all looking at it. And then your hard drive is like a physical filing cabinet. And if I'm working on a piece of paper at my desk, that's my cache. That's the calculation I'm currently doing. My desk is my RAM, so that's the stuff that's open there. So stuff on the page, I can access incredibly quickly. Stuff on the desk, still pretty quick. It takes a little bit longer. But if I have to physically get up, walk over to the filing cabinet, pull it open, find out the file. I know nobody does that, but we'll imagine you've seen a film where somebody gets the file and goes back to the desk. That's slower. So the slower the memory, the cheaper it is. And if you have an external device, a USB stick, a DVD, a floppy disk, if anybody remembers those, they're much, much cheaper, but they're much, much slower. So what we want to do is we want to store our variables in somewhere that we can get pretty quickly, because we're going to use them a lot in the program. Our variable is essentially that. It is a box. Now, I did not run. Oh, wait, this box didn't get. I don't want. A box of pieces of metal. Always good stuff. Okay, so here's my prop. Here's my variable that I've created. If you think about what a box is useful for, It's useful for storage. It's useful for, I can put something in here. So there's my storage area. I can put something in. Once it's in there, well, it's stored. I can take it out. I can read it. I can put something else in there if needs be. And that's all we get to do with a variable. We can store information, so we can put something into the box. We can read the store information. We can take it out, we can have a look at it and go, oh, it says that, put it back in again. So that's us recalling the results of that calculation. Or we can change the stored information. So imagine it is, if any of you have ever worked in retail, especially in bigger shops, where they have the security gates, they often have these other black sensors which are counters, and they're trying to work out how many, the footfall into a shop so that they can say, well, does that relate to how many sales we had? And a counter is the idea of a variable which is going to change over time. Okay, so I can go and I can go, oh, how many students in the class? Let's say I've got a sensor here. It doesn't tell me I've got 15 students. And then another one walks in, I'll increase to 60. So I'm changing the value of it. And then 10 more walk in, increases to 26. And then 2 people walk out and it reduces down to 24. So each time with that, I've got a storage area where I can hold that information. I've got the ability to read the information out, what are we at now? And I've got the ability to update that information, either by increasing or decreasing, or just changing it completely. It's really, really simple, but it's super useful. If we're to extend the box analogy, think of how successful places like, they're so successful I can't remember their name, storage shops are, where you just go in and you literally a shop to buy boxes. And they're huge, and they have all these different types of boxes. So storage, whether it's a box or a bag or a rucksack, is something that everybody needs. Everybody can see a use for it, and our programs are no different in that sense. To create our storage area, we need 3 things. We need a data type. The data type is going to explain to us what type of things we can put in that box. When we create a variable, we say, hey, the data type is whatever it is. That is an indication to the program to go off to the RAM and to reserve a certain amount of space. We need a name. That's our reference point. So that if we want to refer to that storage area later on, because we might have more than one. I've seen student projects where there might be 100 variables or storage areas in the program. So I need a way of distinguishing between one and the other one. And we need a value. If we're making a storage area, we better use it. We better put some value in there. So let's have a look at each of these. The data type is what type of information it can hold. Programming languages have lots of different data types. And if you've done programming in the past, you will see that some of them on the next slide are familiar and some of them might be unique. Different programming languages have different types of variables. Some are specific to programming languages or to libraries inside programming languages. We're going to use a tiny subset. I'm going to show you about 8, and of those 8, we're only going to use 4 this year. And then, we'll use 4 of these this year, and then we'll have 1 extra one later on. Okay. Here are some examples of data types. So the data type is on the left-hand side, and the space it takes up in memory is on the right-hand side. So we can have a Boolean value. Okay, so a Boolean value is a value that's either true or false. We can have a byte. A byte is made up of 8 bits. It's your unit of information in a computer in that sense. We can have a char, which is short for character, which is 2 bytes. Short, int, and long are all numerical data types that only hold whole numbers. They only hold integral numbers. Int is the most common one. It's short for integer. Short is half the size of an int, and long is twice the size of an int. So again, from that idea of efficiency of keeping your program as small and as compact as possible, you may realize that some of your programs, because of the constraints of whatever you're running it on, might need to reserve space. So rather than using integers, you're using shorts. Or you might have really big calculations where you have massive numbers and you might need to use a long. All of the numerical data types have limits. They are not unlimited numbers. The integer data type
goes from, and I can never remember the exact number, but it basically goes from negative 2.4 billion to positive 2.4 billion. It's a 32 bit data type. The short goes basically half that, so it's kind of 1.2 negative to 1.2 positive, and the long is double it, so it's 4.8 negative to 4.8 positive. We will probably run into one program where we're going to exceed the 2.4 billion, and that's just to see can we break something. We'll increase the counter that way. What's really interesting about integers and numerical data types is they're circular numbers. So if you get to the upper number, 2.4 billion, and you go, oh, add 1 to it, it doesn't crash the program. It actually reverts to the lowest negative number, and if it's a counter, it keeps counting up, which is something you need to pay attention to. But we'll come back to that later on. And then float and double are our decimal point numbers. Float is short for a floating point number, and double is double the size of an integer. So we have all of the space on the integral side that an integer has, and we have an equal amount of space on the decimal side to hold decimal point numbers. The reason why we have two different ones here that basically do the same thing is the float, and again, it's reserved. It's called float because it's for floating point numbers. Is an implementation of decimal numbers that allow the decimal point to float. So if we've got a really big integral part and it's only like that's whatever 2.3 billion, 0.1, it can reserve a lot of space for the whole number part and a really small amount of space for the decimal part. But if we use a number like pi, 3 point, and we have a huge amount of information in the decimal part, it can shift that decimal point the other way. You will, in computer hardware, in the second semester, if Paddy's doing the same syllabus that when I taught it last, actually look at the engineering specification for floating point number, because they have to explain how they're able to shift the number up and down and how they can manage that in the computing space. If you've done programming before, depending on what language you've done, the language may use this float as its default decimal number type. For Java, we use double. If you want to use a float, you need to write float, the name of whatever you're calling your variable. And when you give it the value, it needs to have an F after the number, because otherwise it just assumes it's going to be a double, and that can lead to kind of communication error issues. For a double, so it's in Java, a double is our default decimal point number. If you've done something like C#, then a floating point number is your default decimal number. Just to kind of keep it aware. But we can use both if it was required. For us, this year we're going to use Boolean, we're going to use character, we're going to use integer, and we're going to use double. We're not really going to look at the others. They're there, you can use them if a project dictates, but really for all the examples we'll work through, that's the 4 that you would need. Okay. Might get to do too much practical work at the end of this. Not too many slides. Okay. When you're naming the variable, so the first thing is you give it a data type. The second thing you do is you're going to give it a name. A name is how you're going to identify it later on. This is my counter variable. This is my age, if you're, let's say, building a Java program to model a person. This is my address. This is the make of the PC. This is the size of the hard drive. And so you're going to give it some sort of a useful name. I still see 4th year students. So they've been through 4 years of programming, probably about 6 modules in total of programming, declaring variables. Oh, I've declared my variable. What did you call it? Oh, I called it IX11. Okay, what does that mean? Oh, I don't know, I just typed some keys. Whenever you give a name to something in programming, whether it's the name of your program, the name of a variable, or what we'll see in December, the name of a method, it should have a sensible name. That's for your benefit. The computer doesn't care. You can give it a ridiculous IX1111AB as the name. The computer will be able to work that out. That's not a problem at all. But for you, the human, the person who has to read the code, the more sensible the name, the easier it is to understand what's happening, the easier it will be to go, oh, I can see what that variable is doing, and I can see where it's going. Because our programs at the moment are 10, 15 lines of code. What if you have a 10,000 line program, and you've declared a variable all the way up at the top of, let's say, line 7 or 8. But the section of code you're looking at is line 700. And you come across a variable you don't understand. Without a sensible name, you need to go back up to the top and start reading down through all of that code. If you remember the Millennium Bug, this whole Y2K problem that came around in 99, 98, the reason why, if you were qualified as a programmer at that point, you could charge so much money for fixing these systems, and all the change is, oh, we were using 2 digits for a year, and now we need to use 4 digits for a year to allow it to go over from 99 to 00 and not to have toasters explode. The only reason they could charge so much money is because the systems they were looking at, they weren't complicated, but they weren't documented. They were written with the view that no one else bar me is ever going to look at this code. I'm going to write the code for the bank or whomever it is, and it's going to get installed and it'll just run. And if they have a problem with it, they'll come back to me and I'll fix it. So a lot of the consultants I knew at the time who were working, they were charging ridiculous amounts of money per day for a minor amount of code adjustment. But the rest of the time they were writing documentation. They were adding in comments into the program so that the next time someone had to go in and look at it, it actually was tidied up and it was structured well and there was documentation to explain what was happening. So we want to make sure that we're doing that. It shouldn't be a reserved word. Okay, a reserved word, we'll notice then because when we type them out, they change color. Class changes to blue. Public, static, void, they all change color. And you shouldn't have 2 variables with the same name. If you have 2 variables with the same name that are the same data type, so int counter and int counter, the program's going to go, I don't know, it'll crash. If you have int counter and then let's say Boolean counter, that will work, but from a human reading the code point of view, it's really bad practice because it can lead to confusion. So you should always try to have unique names for your variables within that program. You can reuse the names of other programs. Okay, naming. Your name of your variable can be any combination of letters, digits, an underscore, or the $sign, but it cannot start with a number. Okay. Traditionally in Java, we don't use underscore and we don't use a $sign. They're kind of like leftover stuff from other operating systems like C++. And the other, you'll notice the way that I write my names of my programs and the names of my variables, you'll see them, is I use something called camel case, which is all the words are put together. So you might have a multi-word variable. This is my counter or my first counter. The first letter is going to be little, but then the first letter of every subsequent word will be capitalized just to make it easier for you to read. And you'll see that when I'm doing an example. You cannot have spaces in your names. You can't have spaces in the names of the programs you're writing or in the files you're creating. The same with the names of the variables. Anything you're naming and programming, it has to be all one word, no spaces in between. And it can't be a reserved word as well. Okay. So there are the conventions. I'm going to kind of come back to that. What I think we should do now is we should look at an example. So what I'm going to do is I'm going to do 2 examples. I'm going to do one where it'll be not very simple. And then I'm going to put it into a program called Jelliot, which will animate what's happening so we can see the values moving around. And then I'm going to do a more complicated example. So this is going to be called variables. Save as. Okay. And I can get rid of almost all of this. And get rid of that. And I get rid of this. Okay. If I want to create a variable, I need, as I said in the slides, 3 things. I need my data type. To begin with, we're going to start with the simplest data type, which is an int, which just means a whole number. It can be negative or positive, but it'll be a whole number. I need to give it a name.
I'm going to call this counter. And I need to give it a value. Okay. There's my data type. There's my reference name or my name. And here's the value I'm going to take and put into that variable. Okay, so that's how you get a variable on the screen. If I wanted to use that variable, I could put it in here. I would print it to the screen. I could say, I could change the value. I could say counter is now equal to 56. And then I can print it again. I could make a more complicated problem here. So counter divided by 2. And then I can print that again. Okay, so I've got a little bit of manipulation here happening with the variable. I create my variable called counter, and it's an integer data type, so it's only going to hold a whole number. And I give it a starting value of 5. That's my initialization variable. In programming, you have to give it a starting value. If you create a variable and you don't give it a value at some point before you try to read from it, it's going to cause an error. It's going to throw up an error. Okay. The reason for this is inside your RAM. When you finish, so again, remember the RAM is our random access memory. It's our temporary workspace. So if I create a variable that says, "Oh, I'm using this for my program," and it puts a little mark on it, and it uses it, and then when it's finished, it just removes that mark. It doesn't remove the information in that space in the memory. It just says, "Oh, this is free. Someone else can use it." And it's almost like it's like if you go to the canteen and you find a free table, but it's messy. So if someone's left their own crap on that table, and you have to clean that off first before you can use it for your food. That's what you have to do, or that's what the programs have to do. So if I go off and reserve a space in memory, it goes off and goes, "Okay, I'm going to use this," and it wipes, or it doesn't wipe it. But you initializing it, putting a value in at the start, is effectively cleaning that table off and putting your own food down on the table. So that's what we do first on line 3. On line 5, I'm going to print out that. And what happens here is this substitution rule I'm talking about. Counter. Well, counter isn't a string. It's not in quotation marks. And counter is not a literal. It's not a number. So it's, oh, this must be a variable. So it goes back up here. It goes, oh, it is. Let me find the current value. So it goes to the space in memory in our RAM that we've stored it. And it goes, what's the value there? Which at this point in time is 5. And it goes, okay, replace the word counter here with 5. I can't simplify that anymore. So print that out to the screen. And it prints it out. On line 6, we are changing the value of the variable. We're wiping what was in there already, and we're putting in a new value. And then we call the same print command where it goes off and get the current value of counter, which is not 5, but 56. And it'll print it at the screen. Line number 8 is where we can do some interesting stuff. Line number 8 says, take the current value of counter, 56, divide it by 2. And I picked 56 because I know it's going to be an even number division. And then take that result of that and put it into the value of counter. So counter goes 5, 56, 28. If we do this, we take 56 divided by 2, we get 28, put 28 into that box. And then we print that out there. Okay? Does that make any sense at all? Right. Let's run it, make sure it's working, and then I'm going to run it through the animation program so you can see what it looks like. Save. See variables. Good, no errors, and then Java variables. You can see there we have 5, 56, and 28. Now, let me show you a tool that is useful for me as a teacher, might be useful for you to get your head around what is happening in a particular concept, but I would not advise you to use this as a your development environment. Notepad++ is a far better example of this. So here is Jelliot. Jellyit is a tool for visualization of what's happening inside your code. So I'm going to take my code from Notepad++. I'm going to take all the important stuff, copy that, put it in here, and I'm going to delete out these print statements because we don't need them. Keep our code nice and small and compact. Oh, for God's sake. Okay, so I've left all the important stuff here. I've left me creating the variable, setting the initial value to 5, change the value to 56, and then updating that by using the original or using the value of 56, which was held in the variable for a calculation, and then updating the variable based on the results of that calculation. So let's compile this and let's run it. Okay, I'm going to go really slow on this just so you can see what's happening. No, that's not what I want. Step. Okay. So, and the nice thing about Jellyit is, again, it highlights the section of text you're working on. What it's doing now is it's creating a box, say, well, this is your main method. This is the work of your code. Okay. So, we've created a box here called counter of type integer, and I put the value 5 into that. That's my first command. After line 5, that's where our program sits. That's the values inside our variable. If I start it again, it takes the value 56 and wipes the previous value and puts in 56. Okay, everyone with me so far? Okay, so here's the next bit. It's going to take 56, which is my current value. It's going to divide it by 2. Resolve that first. And then with the result of that, it's going to put it back into the box. So until the last part, which is the putting the value back in the box, you could see that the value inside the counter was still 56. And even though we'd finished the calculation on the right-hand side of this, until we actually put the value in there, this value hasn't changed. Now, this, obviously, I've slowed this down massively. It happens almost instantaneously when you run it through Java, the Java command line. But you can see what's happening. This is retrieve whatever the current value is. So it's 56. Finish this calculation. 56 div 2 gives me 28. Put the result of that calculation back into this box here. Right, that line is complete. Move on to the next line of the code. Does that make sense? Does anybody have any questions?
Does it make any difference in speed if the memory is clear or not?
If the which?
If the memory is clear or not?
Not really, no. So, in case you didn't hear the question, does it make any difference if your memory is clear or not? Your memory is never clear once the machine's turned on. The process going from the machine being off to turn on the machine, load up, let's say Windows, load up any of the starter programs you have that would automatically start up, memory is never going to be clear. If we were doing a different language, if you're doing something like C++, you would have somewhere in our first year course a lecture or 2 or 3 or 5 about memory management and about allocation and deallocation of memory, which is basically you tidy up after yourself. Okay, so let's go back to the canteen analog. Deallocation and allocation of memory is what people are meant to do. I'm finished with my food. I'm going to clear the table as I leave. You know that doesn't happen. It's really efficient if it works, but it's not really realistic. What Java has is what the canteen has downstairs. Every now and again, one of the staff members goes around and cleans the table. And this is called our garbage collector. What the garbage collector does inside the Java virtual machine is literally just clean up the memory. Oh, you're not using this variable anymore. I'll clean up that space. You've left this method. I'll remove that. And so what they're doing is they're trying to free up the memory as the program's running in the background. And just like the staff, well, hopefully just like the staff in Arthur's, they try to do it without being intrusive. If it's really, really busy, they don't do it because they'll be bumping into everyone. But as they see a free spot there, I'll go over here on top of the table so more people can come in. And then I won't disturb the people who are sitting at the table. I'm hoping none of you have had the scenario where they're literally taking cups off the table as you're trying to drink from the cup. Okay, that wouldn't happen. And it wouldn't happen with the garbage collector. If you're using the variable, it's not going to get released. It's not going to get tidied up. But if you've finished using the variable, there is a virtual canteen
worker who goes around and cleans up the areas to make sure that there are errors there. And that's how it's managed inside Java and inside anything on the .NET framework, so C# or ASP.NET and stuff like that. Okay, so there's one example. Let's amend this example a little bit. Let's add in extra variables. Where are we? So, edit. I'm going to create two more variables here. I'm going to create another variable called int counter2, very imaginative, and call this 9. And we're going to have int counter3. Okay, so I've added in two extra variables here. I've added in a counter2, which I've initially set to 9, and I've created a variable called counter3, which I haven't set a value to yet. I've left these two lines the exact same. Counter2's new value gets the version or the value of counter when it's after this line here, which will be 28, and we add 5 to it, and then that gets replaced over there. And then counter3's first value is where we take the value inside counter and the value inside counter2, we add them together, and then we multiply the result by 4, and then we put it inside. Okay? So let's run this code again, just so you can see what it looks like. I'm just going to step through it so you can see what's happening here. Okay, so we created the first variable, we're putting the value inside. We create the second variable, put the value inside. I'm going to create the third variable, but we don't end up putting any value inside there. And what happens is we're going to immediately move on to line number 8, which will change the value of the first variable. And then move on to line number 9, which will do this calculation. And then put the value inside counter 1. And then these are the new bits. So counter 2 is going to take this value here and add 5 to it and add the result in here. We have 33, and that gets added into counter 2. And then counter 3 is going to be the value inside counter 1 plus the value inside counter 2. We're going to get the result of that. And then we multiply that by 4. And whatever the result of that is, that gets put inside counter 3. Okay, so you can see what's happening there, that as we are setting values to be assigned to the variables, they're getting put inside those boxes. When we call them on the right-hand side of these calculations, we're reading them out from those boxes so that we can use them somewhere else. We can get that number to use in a different calculation. That seems to make sense? Okay. I'm going to work through one more example. Okay. As it ends up this week, we're not going to have any working time, but next week we'll have a much bigger chunk because I need to leave space for you guys for the worksheet to talk through that. So the example that I want to work on today is, oh, it's not that one. Yeah, no, let's do this one. So on the worksheet, on the practice worksheets question, there is a variables file, and we'll look at question 1. Yeah, no problem. So question 1 says, make a program 2 has, so clearly I wasn't paying attention to that. That has 3 integers, D, H, and M, and display the number of seconds in D days, H hours, and M minutes. For this example, we can assume that we have 1 day, or 1 D, 17 H, 17 hours, and 34 minutes. Okay, what this means is I want the end result to be the number of seconds in 1 day, 17 hours, and 34 minutes. Okay, now I know, because I've done this for full-timers today, that that is 149,640 or 20, I can't remember which. So I know what my output should be. These variables here, I'm going to create to store those values. Okay, because they're the things that can change. The number of seconds in 1 hour never changes. There are 60 minutes in 1 hour, and each minute is 60 seconds, which leaves 3,600. And the number of seconds in 1 day never changes. 24 hours in a day, 60 minutes in each hour, 60 seconds in each minute, leaves us with 86,400 seconds in 1 day. Okay, so I know they aren't going to change, but I'm still going to do as little calculation work me as possible. I'm going to try to force the computer to do as much of these calculations as possible. I'm going to use variables to help me. So we're not going to do it in Jelliot because it's slow, but we will keep hopping back into that to help us visualize stuff we're looking at. But we're going to do it here, and I'm going to save this one as, save as, we'll call this one seconds. Java. Here we're going to call this seconds. With a lowercase. Save. Okay. I'm going to create three variables. That's not what I want to do at all. We're going to have int d, and we'll set that equal to 1. We're going to have int h, we'll set that equal to 17. And we're going to have int m, and we're going to set that equal to 34. Every year when I give this question every single year because it's an easy one to, once you understand what's been asked, it's an easy one to work out the calculation. There is always a confusion on why do I need these values here? And there's at least one student who will give me an output which will just be 24 by 60 by 60 plus 17 right there by 60 by 60 plus 34 by 60. So they put that in the printout statement. And they go, there you go. I'm okay, but you didn't use the variables. So, I didn't need to, like I just wrote them in there. And when we're editing the code, we kind of fall into that trap. I can see, I know all the numbers I need here. If you want different numbers, no problem. I'll open up the code, I'll edit the code, I'll save the code, I'll build the code, I'll make sure there's no errors, and I'll run the code. But what's going to happen next week is we're going to look at user input. And once we've got user input, we have to create programs that will work without us actually knowing what the user is going to enter in for D or for H or for M. Because they might enter in ridiculously big numbers, 100 days, 10 hours, and 2 minutes. But our program should still work. So what we need to do is we need to look at how we can simplify that. Now, in addition to simplifying our code, which I'll show you very quickly what we're looking for. So here we're going to have D multiplied by 24 multiplied by 60 multiplied by 60 plus, which I think I can go there, just to keep it neat. We are going to have H multiplied by 60 multiplied by 60 plus 34 multiplied by 60. Okay, that's our output there. That should give us the correct value. And if I change this, if I turn that to 11 days, it still should give me the correct output for that particular calculation. And if I put that back and I change this to 7 hours rather than 17 hours, it still should work.
Okay, and that's what we want. We want as much as possible in the program we're building for it to be a general problem solver. Now, it can only solve one problem. It can only tell you the number of seconds in a specific number of days, hours, and minutes, but it should work for any combination of days, hours, and minutes. I would assume that if you've got a value for days and a value for hours and a value for minutes, that you're not going to go over 24 hours here, and you're not going to go over 60 minutes here. But you could do 100 days, 70 hours, 304 minutes. It still will calculate that correctly because we know what that calculation is going to be. And that's a mistake. That shouldn't be there. That should be an M. I wasn't using the variable. So let's put it back to the original values. 1 day, 17 hours, 34 minutes. I can make that neater because again, I know that this is the number of seconds in 1 day. That's never going to change. And this is the number of seconds in 1 hour. That's also not going to change. And I can see here that the 60 by 60, I've repeated that calculation. I've done it twice. So I'm going to add in 2 extra variables. I'm going to add in int seconds in hour, and that is going to be equal to 60 by 60. I'm going to add in seconds in day, and that's going to be equal to 24 multiplied by 60 multiplied by 60. So now what I can do here is here I can have seconds in, oh no, that should be in a day. And here should be seconds in an hour. Okay? So now I've just made it a little bit neater. I have the number of seconds in 1 hour and the number of seconds in a day, and so now I can have D, however many days there are, multiplied by the seconds in 1 day, and then H multiplied by how many seconds are in 1 hour, and that's just one number. There's no calculation there, so I'm going to leave it as it is. I can make that simpler again, or more efficient again. Look, I'm still repeating this calculation. So what I could do is I could take away 60 multiplied by 60 here, and just type in seconds in an hour. And what that has done is it has minimized my calculations to the absolute minimum I can get without doing the work for the computer. That's also something that amazingly this year I haven't got, but usually in previous years, someone will sit down with a calculator or a piece of paper and they will work out the result of this, 149,000, and they will just have a system that print 149640. No calculation at all. They've done all the computer's work for it. Okay, we don't want to do that, and thankfully this year I haven't seen anybody do that with my full-time group, and obviously I'm working through this, so I'm assuming you guys aren't going to fall into that mistake. But we have minimized our calculations as minimum as possible. We do this once and then we store it. So we need to find out the number of seconds in the day. We're not calculating this part. We're just saying whatever this value is multiplied by 24. So we've saved one calculation. And here we're not recalculating this again because we have it stored. So we have saved one more calculation. And here we saved another calculation. So we're just retrieving that information. Now, that's a tiny example. That entire piece of program there, I think it's 16 lines in total. Really, really small program. We've saved 4 calculations, which in the grand scale of things, you will never notice. If I run this with all of the most inefficient, where we have to redo the calculation over and over and over again for this program, we are not perceptive enough to see the difference in time between having to do it and not having to do it. But if this amasses into a bigger program, into a 100-line program, into a 1,000-line program, into a 10,000-line program, into a 1,000,000-line program, and a 1,000,000-line program isn't impossible. It kind of is for one person. But a 1,000,000-line program for something like a commercial AAA game that you get on a console, like FIFA or Pro Evolution or Grand Theft Auto, or for something like Microsoft Office, or for something like Mac OS X, that's not an amazing amount of code, 1,000,000 lines. Just think about how many people are working on that and for how long.
if you look at something like, I can't remember the stats for Grand Theft Auto 5, but for Grand Theft Auto 4, they had 330 people working for 18 months. So if you do the math on that, 18 months, and however many days are in that month, and however many minutes are in that, and how many seconds are in those, multiplied by 320 people, and imagine they were all writing code. That's not a lot of code that everybody has to write per day. That's probably 100, 200 lines of code per day each person would quickly amass to that amount. So if we can say if every person every day can say 4 calculations, that has a massive knock-on effect on how that program runs, whether it's a game or an operating system or a piece of productivity. So it does make a difference. It's not essential for first year, but like with so much of the stuff we're looking at this year, it starts to build the habit. Why redo the calculation if I can store the results and reuse it somewhere else? Which means if we get to second year, we get to third year, we get to fourth year, your code is naturally efficient because you're thinking about this stuff from first year when it's trivial, when it doesn't make a difference. So that when it starts to make a difference, you don't need to worry about it because you're instinctively doing it. The other thing which you should start instinctively doing is look how I'm laying out my code. If I go back up to the top, I'm aware I haven't run this code. I'll do that in a moment. We have class here, and every time I open up a curly brace, I'm going to go in one space. And I open up another curly brace here, so I go in, I tab in another space. And all of these lines of code here are in the same column because I haven't opened up any more curly braces. I know my printout statement is formatted here, but that's just so that you can see it on the screen. Otherwise, I would have left it out in one line. And then as I come down to where I close it off, when I close in the brace, I come back out. When I close in the brace again, I come back out. This is called indentation. It is purely for you, the human, to make the code easier for you to read. However, not doing it has a knock-on effect. The first knock-on effect is you will lose grades in your assignments from me. In every assignment I give out, not the worksheets usually, but in the actual assignments, indentation counts for somewhere between 3 to 6% of the grade. Is it indented? Is it formatted well? Does it look readable? More importantly, because you can get you first year with terrible indentation. You probably can get you up to fourth year with terrible indentation if your code is really good. But if you write your code like that, and we have a really big file, and even that's not too bad, but the bigger the file gets, the more awkward this gets. You won't remain employed. You will lose programming jobs because you won't adhere to the style of wherever you're working. Most companies, big companies anyway, they have what's called a programming style. And what the programming style is you have to declare variables in a certain way. You have to indentate. Where you open your brackets and leave them, do you leave them here or do you move them on to a next line? There's usually like a style sheet for doing that, and you need to adhere to that code. I know in Gemma's class with client-side web development, she will want you to indent as well. So it's a good habit to develop because now it's tedious, but our programs are really small. But at the end of first year, hopefully it'll be natural. You won't think about it, you'll just do it automatically. And then you won't need to go back and retrofit the indentation into it. The worst thing is when I get a third year student or a second year student who's written a big program, 100, 200 lines of code, and it looks terrible, and they ask me a question. I've spent so long looking at code like this that I can't read poorly indented code. So I will start at the top line and I will start indenting the code. I can spend 10 minutes doing that before I answer the question because I can't actually see the problem. Okay, again, it's a human problem. It's more readable when it's in that shape. Make it easy on the humans that look at your code, whether they're the ones who are grading you or the ones who are paying you. Okay, let's test this. So let's save it, and hopefully all of my messing around hasn't killed something. So there's my command there. Go to command prompt. Open it up. CD. What's that? What did I call it? Seconds. Seconds. No, it's Java C, isn't it? Seconds. Brilliant. And I've got an error. That's good. Let's see what the error is. Can't find symbol sec. All right. Oh, look, that's why. Because I must have
Control Z it back too far. So seconds in an hour. Nothing there. I think that's all. So let's save it. Go back in. Let's recompile. And just before I go run it, notice what I did there. I found an error. I don't know why I'm pointing at this screen. You can't see it. I found an error. I went back in. I edited my code. I saved my code. And then I rebuilt the file. And now that I see there are no errors, I'm able to run the file. So it's that 4-step process. Write your code, save your code, run your code. If you get an error, go back to step 1 and repeat. And you keep doing that until you get no errors. And then you can do step 4. And again, that's a habit that you'll build up over time. So seconds class. And we're left with there. 149,640 is the number of seconds in 1 day, 17 hours, and 34 minutes. So let's go back in here and edit it. Let's say 10 days, 107 hours, 340 minutes. Save that. Compile it. Run it. We are left with 1.26 million. Well, that's a poor reading. 1,269,600 seconds in that many days, hours, and minutes. Okay? Does that make sense? The next step to this, and whenever you're looking at a programming problem, think about what the next step might be. The next step for us is adding in user input. It's what we're going to look at next time. When we add in user input, we don't know what values the users can enter in there. We could have, kind of makes it silly, but we could have negative values in there. Let's say the user's not been helpful and they enter in a negative value. We get a greatly reduced number because all of the hours were negative. So they were subtracted away from the total. Okay? We can also, once we start getting user input, we have to build in contingencies to make sure that the user enters in the values they're meant to enter in. But we'll look at that next week. I didn't send around the attendance, so that's fine. I will see you all next week. Have a good evening.